Hello everyone, I hope you have been enjoying your Thanksgiving break. And now that break is almost over, I thought to record a video for you guys that I'm explaining materials of each chapter so that you'll be prepared for your makeup exams. So I start with chapter 1 and 2, which are the materials for exam 1. So as I told you, I'm just going to ask you from these study guides. But there is some confusion from some students that how to study these, or like they thought that not all of these materials are important. So I thought to just review them with you. So if you listen to this video and devote the time, you should be good. And I encourage all students to listen to these videos or study the study guides, because in your final exam, you're going to see all these chapters. Okay, all common substances such as soda pop are ultimately composed of tiny particles called atoms. So it's really important to know that everything is composed of atoms. I can ask you that in the exam. Atoms are so small that a single drop of soda contains about 1 billion trillion of them. So you should have an idea of how small they are. If I tell you that in the droplets of water or like soda, we have 10 atoms, or like 100 atoms, or 1 atom, or 1 billion trillion atoms. You should have an idea of the scale and the magnitude of these numbers, because atoms are so small, so we have like so many of them. In many substances such as soda, the atoms are bound together to form several different types of molecules. So atoms bound together to construct the molecules. Okay. Carbon dioxide molecules consist of 3 atoms. 1 carbon and 2 oxygen atoms. So we say CO2, we have 1 carbon, 2 oxygen, held together in a straight line by chemical bonds. So it's really, and we talked about chemical structures in the next chapter 10 that I'm teaching, but just know that CO2 has like 1 carbon, 2 oxygen, and then they have like, the shape is like a straight. Water molecules consist of 3 atoms, 1 oxygen and 2 hydrogen atoms bonded together, but rather than being straight like carbon dioxide, the water molecule is bent. So we have like, H2O being like this, but carbon dioxide is like this. And we talk about this more in next chapters, but no. H2O is bent, carbon dioxide is straight. The details of how atoms bond together to form a molecule, straight, bent, or some other shape, as well as the type of atoms in a molecule, determine everything about the substance that the molecule composes. So the details of how atoms bond together to form a molecule, such as being like bent or straight or some other shape, as well as the type of atoms in a molecule. Do we have like hydrogen? Do we have like carbon? What do we have? The type of atoms determine everything about the substance that the molecule composes. The characteristics of water molecule makes water a liquid at room temperature. The characteristics of carbon dioxide molecules make carbon dioxide a gas at room temperature. The characteristics of sugar molecules allow them to interact with our taste buds to produce a sensation of sweetness. Think of atoms and molecules as tiny particles that compose all common matter, and chemical bonds as the attached together, and atoms and molecules are tiny particles that compose all common matter, that hold atoms together. So chemical bonds hold atoms. What is pressure? Pressure is the result of collisions between gaseous molecules and the surfaces around them. So I asked you, what is pressure? Or give you this definition, the result of collisions between gaseous molecules and the surfaces around them. And I say, what is the following definition? And I say, is it like pressure? Is it like energy? Is it like force? Is it like density? And you should know this is pressure. Chemicals make up virtually everything we come into contact with. Chemistry explains the properties and behavior of chemicals in the broadest sense by helping us understand the molecules that compose them. I guess I just like this highlighter. There is a direct connection. I meant to use the highlighter. Okay. There is a direct connection between the world of atoms and molecules and the world we experience every day. Chemists explore this connection. They seek to understand it. A good, simple definition of chemistry. So what is chemistry? Is the science that tries to understand how matter behaves by studying how atoms and molecules behave. So I say, what is the following definition? A good, simple definition. So I said, the science that tries to understand how matter behaves by studying how atoms and molecules behaves. And I say, what is the following definition? And I say, this is like chemistry, this is like mathematics, this is like geology, this is like biology. You should say this is like chemistry. Chemists use a scientific method to understand the world. And what is scientific method? Is a way of learning that emphasizes observation and experimentation. Observation, experimentation. And that is scientific method. The scientific method stands in contrast to ancient Greek philosophies that emphasizes reason as the way to understand the world. So the Greek philosophers, they use reason, but chemists use scientific method. And then I say, what is scientific method? Or give you the definition and I ask, what is it? And you should say scientific method is a way of learning that emphasizes observation, experimentation, and is in contrast to reason. The key characteristics of scientific method include observation, the formation of hypotheses, the testing of hypotheses by experiment, and the formulation of laws and theories. This is another thing really important. Just memorize this. The key characteristics of scientific method include observation, the formation of hypotheses, testing of hypotheses by experiment, and the formulation of laws and theories. Combustion means burning. The mass of an object is a measure of the quantity of matter within it. So, I asked you in the exam, what is the measure of quantity of matter? And then I say it is mass, it is like density, this is like pressure, this is like weight. So this is like mass. Hypothesis is a tentative interpretation or explanation of the observation. So what is the definition of hypothesis? We say it's a tentative interpretation or explanation of the observation. I say, what is, tentative interpretation or explanation of the observations? And I say it's like scientific law, is it theory, is it hypothesis, is it like reasoning? And you say that is hypothesis. A good hypothesis is falsifiable, which means that I can give you this as a true or false. Is it true or false? A good hypothesis is falsifiable, which a good hypothesis is not falsifiable. So it would this future testing has the potential to prove it wrong. It means that testing has the potential to prove it wrong. True or false? True. Or I can tell would be then false. Okay. Experiments are highly controlled observations designed to validate or invalidate hypotheses. So I say, what is the following definition? Highly controlled observations designed to validate or invalidate hypotheses. And I say, is it like scientific theory? Is it like a law? Is it like a model? Is it like experiments? Then you should choose experiments. Sometimes a number of similar observations lead to the development of a scientific law, a brief statement that summarizes past observations and predict future ones. So this is really important. What is a scientific law? A brief statement that summarizes past observations and produce future ones. Law of conservation of mass is a scientific law. Law of conservation of mass states that in a chemical reaction, matter is neither created nor destroyed. One or more well-established hypotheses may form the basis for a scientific theory. So that was scientific law. Here we have scientific theory. Theories provide a broader and deeper explanation for observations and laws. So these are like, you should just like memorize this. So one or more well-established hypotheses may form the basis for a, I give this like blank and say like fill this out. And then I say one or more well-established hypotheses may form the basis for this. And I say model for like scientific theories, for like hypotheses, for like observations. So you should fill this out with scientific theories. And theories provide a broader and deeper explanation for observations and laws. Scientific theories are also called models. So what is the other name of scientific theory? Model. Theories are models of the way nature is, and they often predict behavior that extends well beyond the observations and laws on which they are founded. So this is also important to remember. So based on the theory, you have like some observations, and then based on that, as we said, here, remember again the definition of scientific theories. What was it here? One or more well-established hypotheses may form the basis for a scientific theory. And then they are also called model. And, these models, this scientific theory, we have like, when we form a scientific theory or a model, we have them based on some observations and some hypotheses, but then we can predict for other, observations or like behavior, we can predict behavior beyond the specific observations that we had. A good example of a theory is the atomic theory of John Dalton. Dalton explained the law of conservation of mass as well as other laws and observations by proposing that all matter was composed of small, indestructible particles called atoms. Theories are also tested and validated by experiments. So here, theories. Okay, so I say true or false. Theories are also tested and validated by experiments, right? Or I say theories are also tested and validated by reasoning, false. Notice that scientific method begins with observation, and then laws, hypotheses, and theories are developed based on these observations. Experiments which are carefully controlled observations, determine the validity of laws, hypotheses, and theories. So here, experiments, important, remember that. So that's it. Now I will go to chapter 2. Let's see if I can accomplish that. Okay, now we're on chapter 2 and I'm going to use my highlighter. Measurement and problem solving. A unit is a standard agreed on quantity by which other quantities are measured. What is the following definition? A standard agreed on quantity by which other quantities are measured. A unit. So, unit. Units are extremely important in reporting and working with scientific measurements, and they must always be included. True or false? Units must always be included. True. Scientists adhere to a standard way of reporting measured quantities in which the number of reported digits reflects the precision in the measurement. More digits, more precision. Fewer digits, less precision. So if a scientist report a number 1.00, this means something. So they did measurements and now they're accurate up to 2 digits after decimal. So this is what it's saying. Scientists adhere to a standard way of reporting measured quantities in which the number of reported digits reflects the precision in the measurements. More digits, more precision. Fewer digits, less precision. So I can ask you, true or false? More digits have less precision. That is false. More digits have more precision. Numbers are usually written so that the uncertainty is indicated by the last reported digit. So here, this last reported digit has uncertainty. For example, by reporting a temperature increase of 0.6 centigrade degree, the scientists mean 0.6 plus or minus 0.1 centigrade. The temperature rise should be as much as 0.7 centigrade degree or as little as 0.5 centigrade degree, but it is not 1. Does that make sense? So if I tell you that I weighed myself and then I was 110 pounds. If I tell you this, it means that this number, it could be 111 or 109. So this number has uncertainty to it, to the level that we are reporting. But if I tell you, I weigh 110.1, it means that for sure I'm 110, but I can be 110.2 or 110.0. You see what I'm saying? So here, if we say 0.6, it would be whether between it could be 0.55 or 0.5 or 0.7 plus or minus 0.1. We use scientific notation to write very large, such as 14,000,000,000, right? And very small, such as 0.000001 numbers. So we use what? Scientific notation. And I'm going to ask you in the exam. A number written in scientific notation consists of a decimal part, a number that is usually between 1 and 10, and an exponential part 10 raised to an exponent n. So for instance, here, if you want to write this number as scientific notation, as we said, the number should be between 1 and 10, right? So I put 1.4. Multiply by 10 to the power of 1, 2, 3, 4, 5, 6, 7, 8, 9. 10, because here I put decimal point here. So again, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We shift the decimal, right? So here consists of a decimal part, here decimal part, a number that is usually between 1 and 10, and an exponential part, 10 to an exponent, raised to an exponent. To convert, that's why I use like the highlighter. To convert a number to a scientific notation, we move the decimal point either to the left or to the right as needed to obtain a number between 1 and 10. So if you see that like that scientific notation is like 15 multiplied by something, it's not. It should be 1.5. The number should be between 1 and 10. And then multiply that number, the decimal part, by 10 raised to the power that reflects the movement of the decimal point. Scientific notation of, for instance, 5 point, let's just do this example. 5.9, just 5,983. So you write this number between 1 and 10. So you see 5.983, right? Because we want to put this in, write this number between like 1 and 10, right? And now these two numbers should be the same, right? It's another way of representing the same number. So I write 10 to the power of, you see, if I put the decimal here, I count 1, 2, 3, would be 1 to the power of 3, and it would be positive because my number, is like large. It's where I had like 5,983. It's like, if my number is like 0.0, or like it would be like 0.5983, that number I write it as 5.983 multiplied by 10 to the power of 1, 2, 3, minus 3. You see? Oh, wait a minute. Let me write it here. Okay, now my battery is low, so my battery was low, so my pen wasn't writing anymore, so I had to plug in this. Okay, let's go back to this example that I had here. So if I have 0.5983 and I want to write the scientific notation, I write the number between 1 and 10, so it would be 5. 5 is between 1 and 10, but you should write the rest of the number too, right? So it would be like 5.983 multiplied by 10 to the power of, here I put minus. The power is negative because we have decimal point, and our number is between 1, is smaller than 1. Does that make sense? So the power is negative. And you count, you change your decimal point to here, right? So you count how much you shifted. 1, 2, 3. So it would be minus 3. So if I write these numbers like 5.983 multiplied by 10 to the power of minus 3. 1, 2, 3. So, I confused myself here. So if I want to write the scientific notation of this, it would be, oh yeah, you see what I did? Okay. Okay, you see, okay, I should paraphrase. So here, when I put like 5 here, you count the digits. So you write 5.983, and then how much I shifted compared to the, so decimal was here previously, I shifted to here. So I moved it by 1. So it would be 10 to the power of minus 1. Yes, I'm confused myself here. So forget what I said here, but for here, 0.5983. You write the number between 1 and 10, so it would be 5.983 multiplied by 10 to the power of, so you shifted this decimal here. How much you shifted? 1. So it would be 10 to the power of minus 1. And if you want to do this calculation, would be like 0.983. right? And for like 5983, it would be like 5.983 multiplied by 10 to the power of 3. Because you put like 3 zeros and then you have like 3 decimals, so it would be like 5.983. And you know that the zeros after this decimal, we can just cancel that if we're just writing, for ourselves. If someone reports you a number like this, you cannot omit this 0 because it means that it has this much of precision. So now, for some reason, the equations doesn't show in Weebly, but I downloaded the file from my laptop and it's working fine. So the scientific notation of 5,983 is like 5, I guess I write it here, 5.983 multiplied by 10 to the power of 3 that are big, like here, I guess for like, for 5,983. Here, when I want to write the scientific notation, I put like 5.983 and then I count, where I shift the decimal, and I count here, 10 to the power of 3. But for scientific notation, I feel like, let me open the chapter 2 study guide in my laptop. Okay, and for this one, as I said, we write the number between 1 and 10, 3.10. Multiply by 10 to the power of negative, because you see the number is much smaller and, the number is smaller than 1, so we have like negative. Remember, 10 to the power of minus 3 equals 1 divided by 10 to the power of 3. So it's equal 1 divided by 1,000. So here I move the decimal here and I count how much. 1, 2, 3, 4. So for number here, I count how much I shifted from the decimal point and then write it negative. Remember, large numbers have positive exponents and small numbers have negative exponents. I can ask you from true or false. Large numbers have negative exponents and small numbers have positive exponents. False. Measured quantities are written to reflect the uncertainty in the measurements. If a measurement about gold is rough, we could describe the bar as counting 10 grams of gold. If a more precise balance is used, we can write the gold content as 10.0 gram of gold. We could report an even more precise measurement as 10.00 grams. We report scientific numbers so that every digit is certain except the last, which we estimate. For example, if a reported measurement is 54.872, we know the last 4 digits, which means 5, 4, 8, 7, are certain. The last digit, 2, is estimated. So this is estimated. Okay, here I have a typo. The first 4 digits are certain. The last digit is estimated. Significant figures. The non-place-holding digits in a measurement are significant figures or significant digits. So what is the definition? I asked you, what is the definition of significant figures? The non-place-holding digits in a measurement are significant figures or significant. Significant figures represent the precision of a measured quantities. So I asked you, which one represent the precision of a measured quantity? Scientific notation, significant figure, or like reasoning, I don't know, some other options, but significant figures represent the precision of a measured quantities. The greater the number of significant figures, the greater the precision of the measurement. I can give you this as true or false. The greater the number of significant figures, the greater the precision of the measurement. Significant figures represent the precision of a measured quantity. To determine the number of significant figures in a number, we follow these rules. All non-zero digits are significant. For instance, 1 and 5 in 1.05 and then 0.0110. All non-zero digits are significant. And I asked you this, just like memorize, remember. Interior zeros between two numbers are significant. Zeros between numbers. Trailing zeros to the right of a non-zero number that fall after a decimal point are significant. For instance, 0 in 5.10 and then 0 in 3. Trailing zeros that fall before a decimal point are significant, like 50.00 and then 1700.24, like these two zeros are significant. Leading zeros to the left of the first non-zero number are not significant. They only serve to locate the decimal point. For example, the number 0.005 has only one significant digit. So I will ask you how many significant digit 0.0005 has. Then I say 1, 2, 3, 4. So you should say 1. Why? Because as we said, leading zeros to the left of the first non-zero number are not significant. So I say leading zeros are not significant. True or false? Leading zeros are not significant. That is true. Or I ask you, leading zeros are significant. False. Trailing zeros at the end of a number but before an implied decimal point are ambiguous and should be avoided by using scientific notation. Trailing zeros at the end of a number but before an implied decimal point are ambiguous and should be avoided by using scientific notation. For example, it is unclear if the number 350 has 2 or 3 significant figures. We can avoid confusion by writing the number as to indicate 2 significant figures or 3 significant figures. So can you tell me that how we can write this number 350 so that it has 2 significant figures? Right. 350, so it has 2 significant figures. You can pause the video and write it yourself. So if you write it as 3.5 multiplied by 10 to the power of 2, this number has 2 significant figures. But if we want to write it as it has 3 significant figures, we write it 3.50 multiplied by 10 to the power of 2. And it has 3 significant figures. Okay. When a number is expressed in scientific notation, all trailing zeros are significant. Remember. So here, you see, this 0 is significant. That's why it has 3 significant figures. 3 significant digits. Okay. Exact numbers have an unlimited number of significant figures. Remember, I tell you true or false. Exact numbers have an unlimited number of significant figures. Exact numbers originate from these sources. I'm going to ask you in the exam. Just remember this. I'm just telling you. Exact numbers originate from these sources. Exact counting of discrete numbers. For example, 3 atoms means 3.0000 atoms. So exact count, if I say we have like 250 students in the class, that is an exact number. Define quantities such as the number of centimeters in 1 meter, because 100 centimeter is defined as 1 meter. 100 centimeter equals 1 meter, means 100.000 centimeters equals 1.000 meter. So define quantities. Integral numbers that are part of an equation. For example, in the equation, which, as I said, for some reason the equations are not printed here. In the equation, radius equals diameter divided by 2. 2 is exact, and therefore has an unlimited number of significant figures. When we use measured quantities in calculations, the result of the calculations must reflect the precision of measured quantities. We should not lose or gain precision during mathematical operations. Multiplication and division. In multiplication or division, the result carries the same number of significant figures as the factor with the fewer significant figures. So, when we have multiplication and division, the result has the same number of significant figures as the factor with the fewer significant figures. So, if we, say 5.02 multiply by 89.665, here we have 3 significant figures, here we have 5 significant figures, and then here we have like 2 significant figures. So at the end we should have 2 significant figures, the one with the fewer significant figures. So you put these numbers in the calculator, and then when you want to write the number, you write it with the one that has fewest or like smallest significant figures. And just like email me, ask me any questions you have. I'm just trying to make this video as short as possible so you see it. Okay, I guess I choose this number, this color. Rounding. When we round the correct number of significant figures, we round down if the last or leftmost digit dropped is 4 or less. We round up. So basically, we round the correct number of significant figures in rounding. So what is rounding? When we round the correct number of significant figures, we round down if the last or leftmost digit is like 4 or less. We round up if the last or leftmost digit dropped is 5 or more. For example, when we round each of these numbers to 2 significant figures, so 2.33, so here the number, this one, right, the last or leftmost, here is less than 5, so we round it like to 3, right? But here this number is more than 5, so we round this number 3 to 4. We add 1. So 2.34 would be 2.3, 2.35 would be 2.4. So if I give you like 2.12, here you look at the number, the last digit, because it's less than 5, you just write this as 2.1 if I want to, write like 2 significant figures. Or if I give you like 2.57, because this number is more than 5, you round it to 2.6. You round up. For calculations involving multiple steps, we round only the final answer. So I don't know how to emphasize that. For calculations involving multiple steps, we only round the final answer. We do not round the intermediate results. This prevents small rounding errors from affecting the final answer. In addition or subtraction, the result has the same number of decimal places as the quantity with the fewer decimal places. For example, for subtraction and addition, we consider decimal places. We don't work with significant figures anymore, just decimal places. You count like 2 decimal places, 3 decimal places, 3 decimal places. So you put the number in a calculator, and we want to write it with like 2, as we said, with the fewer decimal places. So it would be 9.21 because it has like 2 decimal places. Remember, for multiplication and division, the quantity with fewer significant figures determines the number of significant figures in the answer. For addition and subtraction, the quantity with the fewer decimal places determine the number of decimal places in the answer. In multiplication and division, we focus on significant figures, but in addition and subtraction, we focus on decimal places. I'm going to ask you in the exam. True or false? In multiplication and division, we focus on decimal places. False. In addition and subtraction, we focus on significant figures. False. Just memorize this sentence. Calculations involving both multiplication, division, and addition, subtraction. In calculation involving both multiplication, division, and addition, subtraction, we do the steps in the parentheses first. So first, parentheses. Determine the correct number of significant figures in the intermediate answer. Then complete the remaining steps. So we do the steps in parentheses first. Determine the correct number of significant figures. Determine the number of significant figures in intermediate answer. Then complete the remaining steps. For example, do the steps in parentheses first. Okay, so it doesn't show my example. So I'm going to write it down here. Let me see which example I gave you guys. Okay. 6.78 multiplied by 5.903 multiplied by 5.489 minus. Okay. Do the step in parentheses first. First, we do this. Use the subtraction rule to mark here for 0.479, right? You just put that in calculator. And here you see that we have like 2 decimal. So we write this number as, so here we have like 2 decimal places. Because 5.01, the number in the parentheses with the least number of decimal places, has 2. So remember, we should have like 2 here, right? 2 decimal places. Then perform the multiplication and round the answer to 2 significant figures because the number with the least number of significant figures has 2. So remember here, when we count the number of significant figures for each of these, this one, because we have like when we write the number, so basically we should have write this as 4.78, yes, 0.48, I cannot count, 0.48. But remember, we do not round the number, right? We round at last. So here we just we don't round. But remember here, if we just consider 2 decimal places, our number would have 2 significant figures. So here, because we're dealing with multiplication, the least number of significant figures is corresponding to this number here, but we don't round it, we round at last. So what we do is that we write like 6.78 multiplied by 5.903 here, multiplied by 0.479, but this one has like two significant figures because here we should consider that if this calculation was just by itself and we wanted to round it, we would like write 4.48, but we don't round because we round the final answer. But we write this number here, but the final answer should have two significant figures, so we just write 19 because this one has like two significant figures. I hope it's clear. If it's not, just email me, ask me, I explain to you. By themselves, numbers have little meaning. For instance, in the sentence, when my son was 7, we walked 3, this sentence is confusing. We don't know what the numbers mean because the units are missing. The meaning becomes clear when we add the missing units to the numbers. When my son was 3 months old, he walked 3 steps. So remember, if I say we can just write numbers by themselves, this statement is wrong because you don't know what I mean. In chemistry, units are critical. Never write a number by itself. Always use its associated units. Otherwise, your work would be confusing. The two most common unit systems are the English system used in the United States and the metric system used in the most of the rest of the world. The English system uses the units such as inches, yards, and pounds, while the metric system uses centimeters, meters, and kilogram. Okay, I'm going to ask you this, so just remember. English system, we have English system is used in United States, metric system in the rest of the world, and then English system has inches, yards, and pounds. Metric system has centimeters, meters, kilogram. And I'm going to use another color. Never write a number by itself. The most convenient system for science measurements is based on the metric system and is called the International System of the Units, or SI units. What is SI unit? I'm going to ask you. SI units are a set of standard units agreed on by scientists throughout the world. The base unit of length is meter. The base unit of mass is kilogram. The base unit of time is second. So if I tell you the base unit of time is hour, that is wrong. If I tell you the base unit of mass is gram, it's wrong. If I say the base unit of length is centimeter, is wrong. Just remember this. Each of these base units was precisely defined. The kilogram is a measure of mass which is different from weight. The mass of an object is a measure of the quantity of matter within it, while the weight of an object is a measure of the gravitational pull of the matter. So I'm going to ask you this, what is mass, what is weight? Measure of the quantity of matter within it is mass. Weight of an object is a measure of the gravitational pull of the matter. Weight depends on gravity while mass does not. True or false? Weight depends on gravity in the same way that mass depends on gravity. False. If you were to weigh yourself on Mars, the lower gravity would pull you toward the scale less than Earth's gravity would, resulting in a lower weight. So weight depends on gravity. A 150-pound person on Earth weighs only 57 pounds on Mars. However, the person's mass, the quantity of matter in their body, remains the same. A second common unit of mass is the gram, defined as follows. 100 gram equals 10 to the power of 3 gram equals 1 kilogram. The SI system employs prefix multipliers with the basic units. These multipliers change the value of the unit by powers of 10. So, SI prefix multipliers. So remember, especially these ones I'm going to ask you. Micro is 10 to the power of minus 6. Nano is 10 to the power of minus 9. Centi is 10 to the power of minus 2. Milli, 10 to the power of minus 3. Deca, 10 to the power of 1. It's like decade. 10. Remember. Deci, 10 to the power of minus 1. Kilo, 10 to the power of 3. Mega, 10 to the power of 6. Tera, 10 to the power of 12, like terabyte. Giga, 10 to the power of 9, gigabyte. Hecto, 10 to the power of 2, so hecto, 10 to the power of 2. Pico, 10 to the power of minus 12. And femto, 10 to the power of minus 15. Remember, just remember, it's kilo, especially important. Giga, nano, milli, centi, deci, deca. Just remember this. A derived unit is formed from other units. What is a derived unit? For example, many units of volume and measure of space are derived units. Any unit of length with cubed raised to the third power becomes a unit of volume. Therefore, cubic meters, cubic centimeters, and cubic millimeters are all units of volume. We also use liter and milliliter to express volume. So I tell you which one of the following is not a unit of volume. Milliliter, cubic meter, cubic centimeter, and kilogram, right? So what is a derived unit? Is formed from other units. Kilogram, mile, meter, inch, yard, foot are units of length. Kilogram, pound, gram, ounce are units of mass. Kilogram, pound, gram, ounce, unit of mass. Kilometer, kilometer, mile, meter, inch, yard, foot, unit of length. Liter, milliliter, cubic centimeter, quart. US gallon are units of volume. So just remember this. Using units as a guide to solving problems is called dimensional analysis. What is dimensional analysis? Using units as a guide to solve problems. The density of a substance is a ratio of its mass to its volume. And again, it doesn't show in the explain everything software that I have here. So I'm just going to write it here. So density equals mass over volume, or M equals V, and we call that D, density. Density is a fundamental property of a substance and differs from one substance to another. You can diagram convergence using the solution map. So what is a solution map? What we were doing in this course. A solution map is a visual outline that shows the strategic route required to solve a problem. General problem solving strategy. Identify the starting point, the given information. Identify the end point, what you must find. Devise a way to get from the starting point to the end point using what is given as well as what you already know or can look up. You can use a solution map to diagram the steps required to get from the starting point to the end. In a graphic form, this progression looks like given solution map find. And this is funny. These were arrows in what I wrote. Given solution map, find. When converting quantities with units raised to a power, such as cubic centimeters, you must raise the conversion factor to that power. So if you have cubic meter, so for instance, you have 100 meter, and then you want to solve the problem, and then you're converting cubic meter, you have 10 meter, but in the problem you want to raise this to the power of 3. You should also raise the unit or your conversion factor to that power. So if you have for instance 1 mole of carbon is 12.01 gram, and then if you in your problem somehow you want to have that to the power of 3, you also should, have your conversion factor to the power of. Okay. And that is the end of chapter 1 and 2. So I hope you guys all do well on your exam 1. Good luck.